Yes, so to start back this example, we're looking at the relationship between a student's score on a specific exam or a particular course and their overall grade point average. Was the relationship there? Was the strength and what's the direction? So I have computed the values, the totals on this table, which are pretty much straightforward in terms of what's required from the table. So you sum the x's, you sum the y's, you square all the x's and total them, you square all the y's and total them, and then xy, which is x times y, and you total that column. Before you start calculating the actual coefficient, you want to plot the scatter plots. Are you hearing me better now? Is everybody hearing me clearly?
Yes, miss.
Okay, great. So, right, so when we look at this scatter plot, as opposed to the first one we had, we can see a much more clearly defined line or a trend towards a more clearly defined line. The points are much closer together, and that usually indicates the closer the points are together. So usually indication of a pretty strong relationship, and the fact that you can see the line more clearly also indicates a pretty strong relationship. But more importantly, the direction. You see again, this line is going upwards, and so it's an indication of a positive relationship between these two variables. So again, as the score on one course increases or improves, so does the student's grade point average, which is a pretty intuitive, very easy relationship to see, because the more A's you get, clearly the stronger your GPA will be, or as your grades go up on individual courses, so does your GPA. So that was expected. That is expected to be the direction of the relationship. Now, in terms of the strength of the relationship, we apply our formula. And so, again, it's n. Now, if we go back, n, in this case, I know usually when we looked at n in all the previous things we've done, n usually indicates sample size. And in this case, it still indicates sample size, but what it tells us specifically is the number of pairs of values that we have in our data sets. And so this represents information on, we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this represents information on 10 students, their scores and their grade point average, score and grade point average. So n is still the sample size, just that for correlation we will use a smaller sample size because of the nature of the calculation. And so the sample size is basically the number of rows of values in your table. So just to be clear on that, so we know what n represents is the number of pairs or the number of rows of values, x minus, of course, the total. So you have 10 rows, so your n in this case is 10 times the sum of xy. Now the totals we have from our table, what is important is the way the formula is applied. So where you see n times a value, you have to do that calculation, you have to do that multiplication before you do any subtraction. So in this formula, you have to times n by the sum of xy first, which is going to give you 10 times 1,075 will give you 10,750. So you have to times this first, and then you times this over here, 710 times 14, which gives you 9,940. You have to do the two sets of multiplication first before you could do any subtraction. So again, our BODMAS rules, the rules of mathematics, still apply. So you multiply and then you multiply and then you subtract. Now at the bottom of the formula, it's the same operation. N times the sum of x squared. You have to do that multiplication first. So that's, here we see n times 51,750. When we times that, we get 517,500. So you have to do that multiplication, and then we're going to square. So we see 710 squared. When we square that, we get 504,100. So you square and you do the same thing in the next square bracket. And so it's 10 times n times sum of y squared. So it's 10 times 25.5, which gives you 255. And then 14 squared, which is going to give you 196. And so just let me admit the other persons who are trying to get in. Right. So you want to make sure you do all your multiplication. You square what needs to be squared before you start doing any subtraction. So just to make sure we're clear on that, you multiply, you multiply, you multiply here, you square here, you multiply here, you square here. Once you've done those, then you can start doing your subtraction. So you're going to subtract the values at the top, which is going to give you 10,750 minus 9,940 will leave you with 810. And then you subtract at the bottom 517,500 minus 504,100 leaves you with 13,400. And then 255 minus 196 leaves you with 59. So now you have the value at the top. You're going to have to multiply these two values at the bottom. It's going to be 810 divided by the square root of, when you multiply 13,400 by 59, it gives you 790,600. And you have to find the square root of that. So it's now going to be 810 divided by the square root of 790,600, which works itself out to be 889.16. And when you divide 810 by 889.16, it gives you a correlation coefficient of 0.91, which again would fall into the category of very strong. And so this is even stronger than the first one we looked at. We see an almost close to perfect relationship between score on a particular exam and overall grade point average for the student. And so this formula, this topic, like I said, it's not a hypothesis testing topic. We're going to go back to hypothesis when we finish regressions, so we can test the significance of our regression coefficient. But for the correlation, it's association. So this is all the analysis we need to do. Once you've done your correlation, once you've computed this value, which is your correlation coefficient, all you need to say is you comment on the strength of the relationship and the direction. So it's a positive value, as we saw on our scatter plot. We expected it to be positive, and it is positive. So as one variable increases, the other one, as the value of one variable increases, the value of the other variable also increases. So as the score on one exam goes up, the grade point value, the grade point average also goes up. So you have a correlation coefficient here of 0.91. Are there any questions? I will take that as no, but no pending the work you're going to do in preparation for the next class, so that I will get a sense of whether, you understand. But if you're fine, so that's fine, I'll move on. So that is the Pearson correlation. And that is that is appropriate, as we said earlier, for linear and interval data. There has to be interval, and we do the scatter plot to determine whether it is whether the relationship is linear. Now, Spearman's rho is another correlation coefficient. This one is much easier to calculate, but it is only applicable for ranked data on two variables. And so this is where, for instance, you put people into classes. So I think one of your assignment questions looked at socioeconomic classes. So you put people into brackets, and then you assign a rank or a value to each bracket. Now, the importance of that value is just to rank the data. So you can say from richest to poorest, poorest to richest, whichever you look at it at, or you give a scale from totally agree to totally disagree, things like that. So once you create a rank or an order for the values, then you can apply this statistic, because that data becomes ordinal data. So whereas the Pearson coefficient was applicable for interval data, this one is applicable for ordinal data. And the other measures we're going to look at are more applicable for nominal data. And so once you have ranked data, you can use the Spearman's rule. So it's not a situation where you get to pick which one you want to use because which one is easier to compute, but it's entirely dependent on what data you have. That will determine what measure you can use. All data is not the same. So all measures cannot be used for all types of data. So for this one, the first example we're going to look at, it says, imagine you're a sociologist, which most of you are aiming to be, and after long years of observation, you have developed a strong suspicion that the social class of husbands and wives prior to marriage is very similar. So in other words, what you've observed in your community is that people tend to marry within their socioeconomic bracket. So if you're working class, you're likely to marry another working class person. If you're millionaire, you tend to marry another millionaire. If you're below poverty line, you tend to marry within that bracket. So the observation of this sociologist is that people tend to marry within their same social class. And so the suspicion is that the social class of husbands and wives prior to marriage is very similar. So in an effort to test your idea, you obtain a measure of the social class background on 15 couples, and then you rank them. But in this ranking, lower ranking equals higher social class. And I'll give you an example of that. A friend of mine went to Dubai, and he was explaining that you can tell with social class a person is from by looking at the license plate on their vehicles. Not that they're luxury plates, but the more numbers, the more digits on your license plate is the lower your social bracket. So as you get richer, the number of values on your license plate tends to reduce. If you see somebody with one value on their license plate, that person is very, very, very rich. But the richest people have no numbers on their license plate. So you can get a sense of what class a person is in by just looking at not like the value itself, but just the number of values on that plate. So similarly, in this ranking, the lower value means a higher social class. So that was just a related example. So you have the wife's rank, and then you have the husband's rank. The wife's rank and the husband's rank. Now let me go to the formula before I talk about the rest of that table. So to calculate this Spearman's rho, it's 1 times 6 times the sum of these squared. Now, D is
Miss,
what?
1 minus 6 is a 1 times.
Sorry, yes, that's a minus sign. Right. So D is what we get when we minus 1, when we minus these two columns. So it's y minus x, basically. The rank in this column, the rank in this column minus the rank in the first column. So it's y minus x that gives us the, or x minus y, sorry. The rank in the first column minus the rank in the second column. So it's x minus y that gives us d. So if you notice, some of these values are going to be positive and some are going to be negative. So if you just sum this column, it's always going to, the value you're going to end up with is always going to be 0. That's just how it works. And so what we're interested in is not the values themselves, but the square of those values. So we square all of these and we take the sum of these squares. So that's the value that we want. And so we minus the x by the y, we get some negatives, some positives, which is acceptable because we're going to square everything. You square all of it and you total it. So you get, in this case, the sum of these square works out to be 204. And we said earlier that the sociologist took a sample of 15 couples. So we know that our n is 15, and then we have the sum of these squares, which is 204. So it's 6 times the sum of these squared divided by n times n squared minus 1. So it's not a lot of calculation you have to do for this particular statistic. The 1 is on the outside, so that's by itself. So you're going to times 6. We found the sum of these squared to be 204. So it will be 6 times 204 divided by, we said that our n is 15, so it's going to be 15 times the square of 15 will give us 225 minus 1. So it's essentially 15 times 224. So when we times 6 by 204, we get 1224. And we divide that by 15 times 224 gives us 3,360. And when we divide the 1224 by the 3360, we get 0.36. And then we minus that from the 1, and that gives us 0.64. Which is not a very strong relationship, but it's moderately strong. We'll go back to our ranking to see where exactly this value 0.64 will fall. But I want to go over the calculation. So you have one, when you do this, when you calculate everything on this side of the formula, then you minus it from the 1. So the 1 stands alone until you get to the bottom here. So it's, again, it's 6, and the 6 will remain regardless of what value your data, how many values you have in your data set. So it's 6 times the sum of these squared, and the sum of these squared we get when we minus x from y, we square those values and we total them up, just to repeat. So it's 6 times the sum of these squared divided by n times n squared minus 1. N being, again, the number of pairs of values that you have. So this particular researcher collected information on 15 couples. And so N is 15. And then we square the 15, which gives us 225 minus 1. And so at the top, it's 6 times 204, which gives us 1224. And then 15 times 224, which gives us the 3360. We divide these two values, we get 0.36. And now we minus it from the 1, and we get 0.64. So, is this kind of sort of clear how you calculate this Spearman's rule?
Yes, Miss.
Okay, great. Now, of course, to get fully comfortable with this, you're going to have to do some calculations. So I'll send you some questions to practice. And so our next class will be more of a tutorial discussion where we look at what you've done You can either share your screen or put on your video and talk us through what you did. And so we can get a sense that people are comfortable with the calculation. Right, so similar to what we did with the Pearson, we're going to also take a scatter plot here. And if we look at this scatter plot, it's very sporadic. It's the values, they're generally going up, like they're kind of close together, but it's very, very scattered. So just looking at this, you can tell that the relationship will not be as strong as the others that we looked at in the previous examples. So this is just a bunch of random values. And so I want to go back to that slide, this slide with the ratings. So 0.64 is strong, but it's barely out of the moderate range. So it is a strong relationship. It's not a very strong relationship. So the sociologist can conclude, I mean, he'll have to do a lot more work on this data, but he can conclude that there is a strong relationship between the social class of husbands and wives prior to marriage or before they get married. Or there is some amount of evidence to indicate that people tend to marry within their social class. And again, these are other examples, excuse me, these are other examples of variables that you might be interested in studying. So again, for the next class, I'm very interested to hear your presentations on variables that you would be interested in looking for a relationship between or among. And so as a sociologist, you really have no bounds in terms of the variables you can study. The entire social sciences at your disposal. So you can look at human behavior in general, consumer behavior, producer behavior, parents, children, students, the pretty much all the variables are at your disposal. So you can use your imagination as widely as you feel. Uh, don't feel restricted in any way. So think as broadly and as widely as you want. So the things that you're curious about, the variables that you're curious about studying, and let us hear what you come up with. So right, so again, the values here can be between -1 and +1. So when the pairs are in perfect agreement, you get either a -1 or a +1. Like I said, it just depends on the direction of the relationship, but that's the only thing the sign is important for, telling us direction. But once it's a 1, we know it's a perfect agreement. And so if it's 0, then there's perfect disagreement. There's no relationship between those. There's no association between those pairs of values. And so it's a measure of the extent to which the two sets of ranks are in agreement or disagreement. And that would tell you about the level of association between them. And then the second example, a sociological study involved the ratings of teachers. Just let me get some water, so 1 second. Yes. So a sociological study involved the ratings of teachers. In order to determine the reliability of the ratings, the ranks are given by 2 different sets of observers, and those were tabulated. And the question is asked, are the ratings reliable? Now, when we're testing for reliability in research, we're looking to see whether when applying the same tool, when more than one people are applying the same tool, do we end up with the same or very similar values? If we do, then we have reliability. If we don't, then we don't have reliability and we cannot use that data, or we cannot rely on that data. So reliability in this sense has a very specific meaning, and it has to do with the level of agreement, the level of similarity, the level of uniformity we get when we apply, when we have different people apply the same tool. If we don't have that agreement, then it means that a lot of subjectivity is going into the ratings, whereas it's supposed to be objective. And so the values that we have, so the ranks, the teachers were ranked by two observers, observer A and observer B. And so you have the scores here for observer A, and then you can observe the scores for observer B. Now, for some of the teachers, we see that the ranks are fairly similar, but for some of them, we see some wide gaps between the scores. And so, overall, what is the level of reliability? And so again, we know that our formula requires the sum of these squared. But to get here, you have to find the d's, which is your x minus y, or a minus b, or column 1 minus column 2. You minus those two, and then you square all of these values. You square them, and you take the total of the squared columns, because if you take the total of this column, you're just going to end up with 0, which you wouldn't be able to use. So you have the ranks, and then you have the sum of these squared. Now look at this plot. This is much more uniform plots than the one we saw in the first example. The values are going up in a fairly uniform way. You can see a clear line here. You have some outliers, but generally speaking, they're all going in the same direction, which is good, which is what you want when you design a tool. You want to design it in such a way that you reduce that subjectivity from anybody who's applying that tool. Anybody could pick it up and use it, and you're supposed to get very similar outcomes. So in terms of the calculation, we see again it's 1 minus everything on this side of the formula. 6 times the sum of these squared divided by n times n squared minus 1. And so in this case, the sum of these squared turned out to be 64, so it's going to be 6 times 64. And in this case, we have 16 pairs of value rather than 15. And so it's going to be 16 times 16 squared, which is 256 minus 1. So when we do 6 times 64, we get 384. And when we do 16 times 255, we get 4080. And when we divide these two, we get 0.0941. And minusing that from 1 leaves us with this. This is supposed to be 1 minus that is just equal to 0.91. This 1 minus is supposed to be out to this point. So the answer here is 0.91. And so with a value like 0.91, which is very, very close to 1.00, we can see that this the ratings given by the two observers are very, very reliable. They're very, very reliable with a value of 0.91. This is what you aim for. This is the kind of thing you aim for when you design a tool, especially a tool like an interview tool or an evaluation tool, an assessment tool that will be used by several people, but you don't want one person rating an individual as a 10 and another person rating them as a 2. That's a very bad tool because it should not allow for that amount of disparity. It should not allow for that amount of subjectivity. And so where you have, just to recap briefly, because I see your time is running out again. Just to recap, we looked at two measures of correlation. Generally, we're looking at measures of association. So far, we've looked at two measures of correlation, which is one of the general classes of measures of association that is strictly applicable to linear data. Linear data meaning data that could be plotted on a graph, and when you plot it on a graph, it looks like it has a general look and feel of a straight line. This general trend towards a straight line. And so we looked at first the Pearson correlation, which is applicable to one type of data, that's interval level data. Uh, and of course linear, so you do your scatter plot to see that it's generally a linear relationship. If your scatter plot is looking like a curve, then you abandon ship and you find another measure, because the correlation coefficient cannot be used if you don't have that straight line. So you have the straight line, you have interval data, you can proceed. The second measure is the Spearman, and Spearman, as we said, is applicable to ranked data. So if you have ordinal data, you can use the Spearman's rule. And a lot of questionnaires we design in such a way that we include a lot of scales, those Likert scales. So you want people to rate something from 1 to 10. You want people to say from on a scale of 1 to 10 how satisfied they are or dissatisfied they are with a particular service or a particular product, or something with their experience, that sort of thing. At the end of the semester, when you ask to rate your lecturers or evaluate your lecturers, a lot of those questions are rating questions, and so you rate. And so when you have those sort of rating questions on your questionnaire, you can then apply the Spearman's rule for testing relationships between those ranks. It has to be ranks, pairs of ranks. Both of the values have to be ordinal. And same with the Pearson correlation. Both of the values need to be interval data, and interval data, that is those values that have the absolute zero. So if you're looking at scores, for example, you can't get a negative score on an exam. You can't have a negative GPA. You can't have less than 0 years of schooling. So those values where those variables where the values cannot be less than 0, that's interval data. Ratio data are values that don't have an absolute 0, so the values can be negative. And so generally speaking, your Pearson, the values in your table, the values that you collect will be positive values, but when you calculate the correlation coefficient, you can get a negative value depending on the relationship, the direction of the relationship between those two variables. And same for the Spearman, you're gonna get positive ratings, but you can get a negative correlation because the two things can be in disagreement. The ratings can be in perfect disharmony, or they can be just in disharmony. So you have that kind of those kinds of things to consider. So I'm going to send you a worksheet with questions, and then I'm going to include in that worksheet that question that you're going to do your 5-minute presentations on. So just look around you and determine what variables you're interested in, and you're going to say which of these two types of correlation would be appropriate for testing the relationship between those two variables. So if you have interval data, you know which one to use. If you have ordinal data, you know which one to use. So you're gonna look back at the PowerPoints, go through this part of the presentation, and then you're gonna come up with your answers. And like I said, be creative, be imaginative, and let's try to make it interesting. So
Excuse me, Miss.
yes.
The last question we just worked in your example where it was 1 minus 0.941. The answer got was 0.059.
No, that can't be. You minus 0.0941 from 1 and get 0.5 something.
0.01 minus 0.941,
It's
and
zero
I got
point 0.0, 0.09.
the last one.
You can't get zero point 0.5 anything from this calculation.
Okay.
Right. So this is the answer. As I said when we went through this example, this 1 minus is supposed to fall off at this point, and the answer is 0.91. You can't minus 0.0941 from 1 and get 0.5 anything. That's just mathematically impossible. Right.
I
So,
saw my error. Thank you.
okay. Right. So we are going to. Are there any other questions or observations?
It's a quick question.
Mm-hmm.
So as long as you follow the principle of x minus y
Yes.
in your D column, it should always total to 0.
Yes. Yes. This column is always going to be total to 0. Once you do this parts correctly, you're going to end up with 0.
Okay.
Great. Anything else? Any other question or observation, concern? How are you coming with your other courses? On track? Somebody there? Oh,
Miss, I'll probably reach out to you if I have any further questions after looking at the presentation again. Need some more clarity by myself.
okay, yeah, so that's why I'm sending the questions because with these statistical things, if it's not hands-on, then it's not very clear from just looking at the presentation that you
Certainly
can
true.
actually do the calculations. So I'm gonna send the questions, and I really am encouraging you to work them so that when you come to the class, you can come with your difficulties and we can work through them, because remember, I'm not there to see you and see what you're doing, how you're doing the calculations, to get a sense of whether it's clear or not. So when I send the questions, please work them, and the next class is going to be entirely a tutorial. So we're going to look at that first question, and then we're going to look at the calculations. The other half of this presentation we're going to do the next time. We're going to do not the next class, the class after that. So Joanna, I'm going to send it in an email. When I'm sending the recording for the class, I'll send the questions in an email. I understand the internet is, I'm breaking up at some points. It's cloudy, so you know what happens with the rain. So I'll send that. All right, so if there are no other questions, we're gonna close here for tonight. Sorry. We're gonna close here for tonight, and I am going to see you all